Thanks again, Jack. That was a very generous and long introduction, and I won't keep you here too long with the food and drinks waiting out there. I'll try to wrap up my story in half an hour. I wanted to, again, thank people who have taken time, Dr. or Dean Alec Gallimore, Dean Munson, and many others here. Thanks for taking the time to come and listen to my little excitement, what I've been up to on shape-changing aircraft wings. The title, as you can see, it's Long Road to Commercialization, and you will see quickly why it's taken that long. And also I want to talk about why getting there can be half the fun. But first let me explain to you I'll tell you what it's about, what is it that we've done, and how I got here working on aircraft wings with no understanding of aerospace engineering. I want to make sure I say that. I see Carlos over there, so I know the difference between lift and drag, and that's where it ends. So for those who are not in aerospace, and of course we all fly airplanes, we see these airplane flaps all the time when you're taking off and landing, and they do a very important function. They create very high lift when the aircraft is moving slowly. So in a way, they actually morph. They extend the surface area and also change the angle of attack. There are many surfaces that you can see. I want to focus on the trailing edge portion of the aircraft wing. But as you can see on the top right, actually when you're cruising, the aircraft, the flaps actually get tucked in. They don't move. But if you think about it, as you go, let's say you're flying from Detroit to London, and about a third of the aircraft weight is actually fuel. And so you're burning fuel, and the aircraft weight is changing continuously, and your operating conditions are changing all the time. The weight's changing, weight's decreasing as you burn the fuel, the altitude's changing, the speed, and at the same time, the actual geometry of the aircraft wing remains fixed because you don't see those flaps moving. If they do, they actually separate the flow, which is not a good thing. That's why they get tucked in. So people have known for a long time that if you could have a smooth continuous surface that can morph, that you can do what's called cruise trim while you're cruising. You can make subtle changes to the geometry of the aircraft wing. You can have significant benefits in fuel efficiency. And there are other benefits too in terms of they're not only changing the camber but also twisting the aircraft wing span-wise. There are many benefits in terms of reducing what's called induced drag and improving performance and so on. So I also want to point out, in addition to flaps, ailerons, as you know, that you do for roll control, that's something actually, this is not a new idea by any means. Wright brothers have actually morphed the wing to, they didn't have ailerons at the time. It's made the Wright Flyer made of balsa wood and fabric. They were able to pull on the tension cables and twist the wing to do the roll control to have a steady flight. But later on, as the aircraft got bigger, heavier wood was used, thicker wood, stronger wood. That was more difficult to morph, so quickly they went to flaps. Ever since, we have flaps as we see them now. The hinged surfaces, I should say, flaps and ailerons are hinged flaps. So what we've done is actually, coming to the end of the story first, is to fly an aircraft with actually shape morphing wing. And that has been demonstrated in the actual flight test. It was in November 2014. And there are many benefits to that, particularly fuel efficiency benefits and performance benefits as well. So if you think about the fuel efficiency, a third of their operating costs almost are fuel costs. It's very significant. And just the US alone, you spend about $60 billion a year on aircraft fuel, on jet fuel. So even a 1% improvement can be significant. And actually the wings and engines have been optimized and to a point where they're extremely efficient. And you can see that there's a significant improvement in the wing efficiency and the aircraft efficiency since 1960s. So it's to eke out any more efficiency, it's difficult. And not only that, as our other expert, Professor Kim Martin, pointed out, that they very rarely fly, they're so perfectly optimized, but they very rarely fly at the sweet spot, so to speak, because of all the other constraints. So one thing to do is that if we can change the shape of the aircraft, that's the next way of improving the efficiency. And that's been, again, known. The figure on the right-hand side, there's a lot of studies done, computational fluid dynamics and other studies done to show by having a variable camber, you can get significant improvement in fuel efficiency. It's not only fuel efficiency is one, but also directly is the environmental impact of the aircraft. And you can see that actually aviation industry contributes about 12% of the total CO2 emissions of all the transportation. Here you can see the note here, a single flight across Atlantic can guzzle up to 60,000 liters. That is more fuel than average motorist used in 50 years of driving. Well, this is probably based on European studies, and I think we can guzzle in less than 50 years. We could probably do that in 20. But still, it's important. The environmental impact is important. So the idea of morphing has been around for a long time, and people have been working on it for at least 50 years now, from NASA, Boeing, Airbus to other universities. And there is a lot of work done in terms of trying to meet these things. This is just a snapshot of some of the mechanisms that are used in shape adaptive wings. And the point is, whatever design we come up with, it has to satisfy, morph it accurately to the desired aerodynamic shapes and remain in that shape under the forces external loads. It should have high strength, particularly fatigue strength. You're talking about a lot of cycles over the lifetime of an aircraft, could be 40 years or 50 years. And it has to be lightweight for obvious reasons. And it has to be reliable for obvious reasons, and also be fault tolerant. If you satisfy 4 out of 5, that's really not 4/5 of the answer. It's no answer at all. You got to satisfy all of those. Oh yeah, by the way, it also has to be easy to manufacture, easy to maintain, and also you have to get the certification. So those are very conflicting design requirements that need to be satisfied. And a lot of that work, I'll come back to this comparison in a moment, but I had no idea about any of this while I was doing my research in the 90s on something related to machine design, kinematics, continuum mechanics, and I was trying to design mechanical motions that do not require any hinges or parts. And you can see in the previous chart, a lot of these designs, in fact, most of them have gazillion parts and a lot of joints. And so I was independently working on developing something like that to have, by exploiting the inherent elasticity of materials in what I call compliant design. And that motivation came originally from the work I was doing here with my graduate students on MEMS, where at the micro scale, the assembly was not an option. You need to produce it in single piece. And the micro electromechanical part of MEMS, what could we do mechanically to get the mechanical motion without any joints, which means without any assembly. That's what led to the idea of compliant design, exploiting the elasticity of the material, so you get the 3D functionality, as you can see here, without having to do any assembly. And a number of these devices were designed and fabricated, tested. The one shown on the top actually tested for 10 billion cycles without failure. We did a lot of work with Sandia National Labs and later on with a company called MEMX for some of the adaptive optics and other applications. So this goes back to the idea of compliance is, look, everything in the engineered world, anything that is strong is also rigid. We associate strength with rigidity. Of course, we want the structures like this podium or the building has to be rigid. We don't want it to sway too much, although you may want it to be earthquake resistant. That's a different issue. So we always design things to be rigid and strong. And we almost avoid elasticity or pretend try to avoid it, but nothing is infinitely rigid. So we can exploit the elasticity and make things to be strong and flexible. Like you see in nature, there are countless examples of things that are strong and flexible. And they also have very interesting geometry to get the right kind of bending stiffness and torsional stiffness so that those leaves don't tangle up in winds. And also they have to operate in all different conditions. The winds blow in every different condition. And some of these devices are very efficient. Something like this comes with a lifetime warranty. And also they have the shape adaptation is another important feature in nature. Somehow, these birds figured out how to fly efficiently under all operating conditions. Here is an example of strength versus flexibility. This is taken from National Geographic video. And of course, 80% of all the living creatures are invertebrates, and you have invertebrate fighting vertebrate there. So you have, even in examples like this, what we have in engineered designs is it's a compromise design. We design things to be efficient at a certain point, whether it's a car running at a specific speed that uses the sweet spot. Anytime you're not operating at that particular speed, you're not getting the peak performance, or every pump in the world is designed to be operating at a specific sweet spot. Same is with the aircraft wings. So if we can do the shape adaptation, we can be efficient under all operating conditions, or more than one operating condition. That's the idea. But then the idea of using elastic deformation is nothing new. People have done that for 100 years. If you look at all the instruments where they have thin flexural hinges, because there's no backlash, you can get very high sub-micron precision. That's been used. And so they're very flexible, but they don't have the load-bearing capacity. On the other hand, if you look at the load-bearing capacity, the structures like this are very strong and rigid, but they have very little flexibility. So what we want is, rather than this lumped compliance, meaning very thin flexural hinges, which work just fine for examples like these, or lid of a shampoo bottle that has to last a few cycles. But if you want load-bearing capacity, you can't have this high stress concentration. So you want to distribute the stresses and strains as uniformly as possible so that every piece of material is sharing the load, so you reduce the maximum stress, and then that will give a significantly improved fatigue life. That's the idea behind distributed compliance that I've been after, working with my students for a while in designing things of that kind. And you can see here, you get large deformation, but the actual strain in the material is in the small fraction of the linear elastic strain, so your stresses are correspondingly small, and you get very high fatigue life. That's the idea. But the question is, how do we come up with the designs like that is always a challenge. But you can see the benefits of doing that. Here is one simple example. On the top left is a conventional windshield wiper. It's got a lot of parts. It has 16 parts and weighs half a pound. Even that good example of how you want something to morph to different contours of your windshield, you put a whole bunch of links and joints to get the mechanical functionality, as opposed to that if you exploit the elasticity of the materials, like a distributed compliance, you get 1/4 the number of parts and half the weight, and performs better. That's the same idea behind these aircraft wing as well. Because of the ITAR restrictions, I can't show the actual structure inside the wing, but you get a sense of looking at some of these examples. We can have the entire shape morphing mechanism is only one piece. So you get very high reliability, and you get a lot of flexibility in terms of the shapes that you can produce. So that is the advantage of having distributed compliant design. And very briefly, in one chart I want to show, because this work started out in thinking about the compliant design in my lab, and a number of students have contributed to it. I'm trying to summarize half a dozen PhDs into one slide. Essentially, on the top left, if you have a conventional gripper, how do you make one-piece compliant gripper? So we have a process by which we capture the design intent mathematically. We want to maximize the displacement where you want it to grasp, and you want to minimize the force it takes to grasp it, and then start with a blank sheet of paper and fill it with a number of nodes and connect them with different beam elements or truss elements, and capture the design objective mathematically and optimize it to come up with the minimum set of elements you need to perform that function. And that's what you see, what's called the topology design. On the first stage, you take the topology and you do your traditional structural size and shape optimization to fine-tune the design so it meets the material constraints, manufacturing constraints, and stress constraints in number of fatigue cycles it has to withstand, and so on and so forth, and then you get the design that way. This is an ongoing challenge, and still is. On the left-hand side, I showed the various methods that we worked on. For some of you who know Professor Noboru Kikuchi, he developed the homogenization method that allows you to come up with the topology of the structure. I initially adopted that method to come up with these kind of compliant mechanisms with very limited success because of the kinds of design we get at the bottom left. And we did many different methods here. I can go into if you have questions about it later on. But I must say that the topology optimization part is still a mixture of art and science. And although at FlexSys, our talented engineers have developed some more sophisticated algorithms to do just that. But the size and shape optimization, to give you an idea, once you have the topology of what the structure should look like, or a jointless mechanism in this case, you can do, you want to maximize the efficiency, or you want to maximize, you distribute the stresses uniformly, you get different kinds of designs. It's the same gripper you can take. If I say I want to maximize the efficiency, you end up with the bottom right picture there, where it tends to give you thin flexural hinges, which is not good if you don't want that. Then if you want to maximize the uniform stress distribution, you get the one on the top right, but of course, like everything else, we want to have our cake and eat it too. You want both, so you can weight your criteria and come up with different design. That's just a snapshot of how we arrive at the design of this jointless mechanism. Now, coming to aircraft. So I was doing all this without any knowledge of aircraft at all until I saw an article one day about what it seems. I thought about, I know how to change the shape of something. I know how to morph things. I don't know what to morph it for. I thought about, having taken the aircraft design course a long time prior to that, I thought of changing the shape of an air. I thought of all these NACA profiles they have, why not have one profile that can change the shape? I didn't know it was a good idea at all. And I put this slide up with 555-1212, and I don't know if many of you are old enough to remember. If you want to get hold of somebody in some town, you get the area code and call the area code 555-1212, and that's how you get the name. That's exactly what I did, looking at the little blurb, and called Wright-Patterson Air Force Base and talked to the guys whose name was there at Pendleton, and told him about how I have a design that I developed for changing the shape of aircraft wing. And I thought he would just hang up on me, but he actually said, come on over, we can talk about it. Actually, he was the lead guy on the mission adaptive wing that they flew in the early 80s. So I went and talked to them, and I did tell them that I'm not an aerospace engineer, but I have an idea. I showed the design about this structural compliance. And to their credit, actually, they had the vision to see that they said, wow, we've been working on it for 30 years, and they showed me the designs they were working on with one of them that I showed earlier that had over 200 parts and nearly 2 dozen actuators. In my case, I had 2 actuators because I want to twist as well, and only 1 part. And they saw the idea that this could potentially work and asked me to apply for an SBIR, and I said, SB what? SB Small Business Innovative Research. So that's how we got started. Many years later, actually, there was an SBIR opportunity, and that led to the first initial $100,000 SBIR helped develop this bottom right, the leading edge. I wanted to demonstrate in the phase 1 that we can build and test the prototype. We rented the Michigan wind tunnel here and tested it and showed actually how you can morph with a one-piece mechanism. So that's what led to phase 2 later on, which then we developed with very talented engineers as we hired at FlexSys, developed various models. This is made out of aluminum that can morph plus or minus 10 degrees and also twist span-wise. So at every stage, we exceeded their expectations, and the work continued from that point on. And we also worked on helicopter rotor blades, where you change the shape of the leading edge of a rotor blade by the time it makes half the turn to prevent dynamic stall, and I can explain that later what that is. And so this is actually made out of titanium. So the point here is that we can make it out of conventional materials. It doesn't require some space-age material. It could be any material like plastics and titanium, aluminum, composites would be fantastic. We can exploit the linear elasticity of the material and come up with the structure that can actually give you the desired deformation, shape, morphing with very few parts. So those are the number of things we've done on the leading edge and trailing edge. We can see we are morphing at 6 hertz in the case of the titanium leading edge and the composite trailing edge up to 15 hertz. Back to fixed wing, that's what I will spend the next few minutes talking about. This was another important milestone, I should say. We developed this beautiful wing on the bottom right, you can see, and attached to the scale composites. You may remember the first X Prize. that went to space and came back, the same aircraft that we used after that because it has enough ground clearance. So we attached our wing that had the drag rake and fully instrumented wing underneath that aircraft and did the flight test. So you've probably seen the video already. And the key part is I want to point out to this chart here. This is the lift versus drag. Essentially, you want to operate at various lift conditions, right? And you want to have minimum drag. Normally, in an aircraft, in a conventional flap, you have increase in drag as you change the lift. This is the actual flight test results that showed that we can have minimum drag as you change the lift conditions. That was a very encouraging result from the flight test. And then the Air Force then gave us green light to go and do a real flight test. And that's what we did with this. We bought a Gulfstream business jet, and we threw away all the flaps and the flap tracks and everything, and designed, built, and installed a shape adaptive wing. And let me just show the quick video of that. This is actually a composite structure that can morph -9 degrees to 40 degrees. And also, this particular video doesn't show the twist, but it also can twist span-wise. And this particular structure, that length you're seeing it can create about 12,000 pounds of lift with a factor of safety of 2. It should support 24,000 pounds of load. So this is a good example of how you can design things to be strong and flexible at the same time. And so this was so we attached this to, let me run this video while I'm talking. Okay, that's good. So this is the flight test that NASA joined the effort. They invested tens of millions of dollars, $30 million or so, into this effort for the flight test. And this one, our talented engineers at FlexSys have designed, built, and shipped it. You can see it right there quickly. They work very fast. They do, actually. And we shipped it to NASA, and NASA did a lot of the instrumentation work and did the flight test. And in every case, what I'm proud of is that all the analysis, from starting with the material validation, especially with composites, and then doing the modeling, coming up with the design, and then verifying the nonlinearities and testing the prototypes and the subsystems and the entire systems, and predicting what it's going to do. And NASA is very conservative. They don't want anything to happen to this aircraft. So we had very thorough validation and verification at every step. And they would actually verify after each flight test compared to what we predicted, and so that we can go to the next level. So they flew they took it to the test. They actually flew it at 2G. They did 2G maneuvers. They actually subjected the aircraft wing to more than twice the dynamic pressure as any commercial aircraft would ever experience. And it worked flawlessly. In fact, we had budget for maintenance and repair, and we didn't have anything to maintain or repair. So it worked beautifully. And they did the test, several tests, or 52 hours of testing over a period of 6 months at 0.75 Mach. And now they are running at 0.85 Mach, high Mach flight tests as we speak now. So what else can I say about? So they had a whole bunch of fiber optic sensors to compare the data at every stage. So that was very successful flight test. And I think I said most everything I needed to say here. And also, they recently completed the acoustic test. I'll come to that in a moment. They also, in addition to all the real-time monitoring, they also have a chase plane, from F-16s to another Gulfstream chasing the aircraft and monitoring everything. So they did a very thorough job with the flight test. Coming back to the first aircraft that Air Force flew in the 80s, that I originally saw the blurb about. This is the F-111 mission adaptive wing. So that was the first time they flew with actually changing the camber and shape adaptive wing. But prior to that, actually Wright brothers did many years prior to that, but they did it for the roll control. And of course, there were other kinds of morphing that was done with actually changing the angle of the, it's more like mechanically displacing the wings for that Bell aircraft. Then there was another aircraft that they flew in the late 90s. This is not actively controlling the shape, but actually designing the aircraft wing in such a way under certain conditions, it will aeroelastically deform to twist the wing for performance gains. So leaving that aside and leaving the switchblade design aside, and also the Wright brothers design, which is actually, that's their key patent, where they actually did for roll control, but primarily for changing the flaps or getting rid of the flaps. If you look at what mission adaptive aircraft did, which is what my discussion with the Air Force people, that's the one they flew. And they demonstrated in the 80s, all the stuff they have known, that aerodynamically they can get significant benefits from 5 to 20% fuel efficiency gains. But structurally, it was too heavy, too cumbersome. As I told you, it's got hundreds of parts and dozens of actuators. And when I actually met them, they told me they were going to take it to Smithsonian on that because that did not go anywhere. But certainly questionable reliability with all the parts and the difficulty to maintain. So what we did is not fundamentally, this idea has been around. The only difference, first of all, we have proven the aerodynamic performance, proven the fatigue strength. We tested this wing for 5 times the cross-sectional shape. We tested it for underload 5 times the number of cycles that an aircraft would experience over a 40-year lifetime. And we tested it for, did not fail until 400% of the maximum load. And yet it is literally lightweight, and it has improved reliability because as far as the shape adaptive mechanism, there's only one part. So the difference is, all I'm trying to get to is that what we've done on one hand is very simple. Here is a design, conventional design that avoids material elasticity, pretend that everything is rigid, and make it very stiff. Whereas this one actually exploits the material elasticity. That's the only difference. And of course, because of this, we get a lot of, NASA being a part of it always helps in some ways, being a lot of press on this. And as Faye Collier mentioned about the actual data shows, significant reduction in fuel burn, and certainly make the future aircraft lighter, more efficient, and quieter. So speaking of quieter, let me also explain here, this is a side benefit. We did not start out with this. This NASA environmentally responsible aviation folks were interested in demonstrating the fuel efficiency and reduction in emissions and reduction in noise. So they saw this as an opportunity to co-invest with Air Force because they see that our technology could do all three, check all 3 boxes. As it turns out, when the aircraft is landing, there's significant noise comes from the airframe, primarily from the airflow around the turbulent flow around the leading edge, the landing gear, and also the gaps between the deflected flap that you see and the fixed section of the wing. Those vortices, they generate a lot of noise. So what NASA at the very beginning asked us to do is asked us if we could actually close that gap through these transition surfaces I'm pointing to here. Those are the compliant fairings on both sides that have to morph in that shape and still be able to withstand the aerodynamic loads. And that's so recently, as of a month ago, they completed, I don't know how many tests they flew over the acoustic array 50, 60 times, or maybe 100 times, Greg, I don't remember now, but those results have shown that they can actually reduce the aircraft noise by 40%, which can be very significant. So with that, now what we are working on is adaptive compliant tab. This is the military KC-135, the aerial tanker, as you can see here. And we are right now retrofitting that with shape adaptive surface. And moving on, I just want to show a picture of all the work that our little company with barely a dozen people, they accomplished. Everything that we've done is actually designed, built, and tested by folks here. And then more recently, we formed a joint venture with a company called Aviation Partners. This is a company that actually installs all the aircraft, the winglets on all the airplanes. So they have significant experience in certification and manufacturing and what have you. So there are a number of surfaces we could morph, although I just talked only about the trailing edge at this point. And here's a simple example of the kinds of things we can morph from the load alleviation surfaces to ailerons and the flaps and the leading edge we can morph. Instead of having the slats, we can also twist it for significantly reduce the wing loading. On the leading edge, we can potentially twist it to potentially for de-icing. That's not proven yet, I don't know, but there are a lot of things we can morph on the wing alone, not to mention other surfaces. But also anything that moves through a fluid, air or water, whether it's an automobile or a wind turbine or a truck or what have you, you can change the shape, you can adapt it to different operating conditions and improve efficiency. So this is the long road I just described, starting from going back to the initial work at the University of Michigan and MEMS and compliant design through all the different stages. Started out with $100,000 SBIR to close to about $70 million in investment. And what I want to point out is that, of course, the motivation for doing this is to turn ideas into reality. That's what engineering is about. But of course, that's just having an idea without resources is just, that's not going to get us anywhere. So we need to have resources, the time and capital, patient capital and patience. And also we need to prove, whether you're working on this or whatever, you've got to prove that it works and it works better than any other alternative. And then we had to make the business case where we need the validation and verification in the real environment. Of course, we need to demonstrate performance, that's a given. Safety is extremely critical for applications like this, and reliability and fault tolerance, all of these, not just some of those, and certainly cost effectiveness. Then, of course, that requires more prototyping, more testing, and whether it's bigger, faster wind tunnels, and requires time and investment. Then certainly finally the flight test that shows the safety verification, and requires even larger sums of investment. So finally we have something that's flight worthy, but that's still not commercialized yet. So then you have to make the business case for a specific application, for a specific aircraft, on a specific mission, and still satisfy all these criteria. Then, of course, you got to do the certification and manufacturing, installation, and warranty, and all of that. Then you had to make the business case for multiple aircraft, for multiple missions, and multiple applications, and start all over again. So that is the long road to commercialization, I wanted to point out, particularly for an application like this, where the safety is critical. People haven't changed the aircraft wings in a long time. We're radically changing the aircraft wing that could make FAA pretty nervous and others pretty nervous too. So, but the point about getting there is half the fun. When I wrote that, I really meant it. It meant it because the fun as in a lot of learning. If it was just an academic exercise, I would still be focusing on kinematics and continuum mechanics of the work that I do in the design and modeling and simulation and optimization. Those are all very important and basic and fundamental. But it goes beyond that. It goes beyond to building prototypes, really good prototypes, and testing, not just materials and prototypes, and fabrication, but also truly designing for manufacturability. But then also, there's a lot of learning involved in patenting, what to patent and how to protect IP beyond patenting. Not everything you have you patent, some things you don't. And at the same time, try not to publish too much on this subject. That is more difficult for us. But then you get to learn a lot about business models, government contracts, audits, and spending other people's money is actually more, what should I say, difficult than it sounds because you're under a lot of pressure to get it right. You want to make sure you deliver more than what you promised at every step of the way. That's the only way we can keep it going. Then on top of all this, we have these ITAR challenges with anything to do with the aerospace. So balancing that and the licensing and learning. So all of this is a lot of learning. But most of all, recruiting really good people who can design, who can build, who can do the modeling, who can do the optimization, who can actually knows how to build real things and test it, and also people who can manage employees and customers and suppliers and contracts and programs. But at the same time, continues to look for new opportunities, new business opportunities, and they all of them pose real engineering challenges. And that's where it goes, brings us back to the real fun, the raw fun of doing engineering. And also I said getting there is half the fun because, especially as a faculty member, we have our day jobs. It's not like our mortgage is at stake if this thing doesn't bend properly. But although we should work like it is, but then we have an incredible job here as a faculty member to afford the time to have a day job that we do teaching and research. And we can still pursue these kind of activities 1 day a week. And we still have 4 days to do other things we do. So that, to me, is a luxury. That's something that we ought to be doing more of. And some of the uncommon features of this project I should point out is balancing the defense and commercial applications. And there's no private investment in that. This is a hard one to get a VC to invest 15, 20 years ago. But we have, well, there's no VC investment means there's no equity loss, which is a good thing. On the other hand, it's all government investment, which is a great thing, but it comes at government speed, which is not very fast. But that's fine. But I think in the end, it's a lot of learning involved, which I believe that it's really something that's extremely important for us engineers. We should be doing. I want to give a special thanks to Bob Gavin, who's not here right now. He's enjoying up north somewhere, but for his legal and business advice, and the very talented engineers who are, some of them are sitting here, who are the ones, they are the ones who turn the ideas into reality, the folks at FlexSys, and for family for putting up with me and with this craziness about this and other stuff. And Air Force for continued support all the way, and NASA for conducting the flight tests. And most of all, University of Michigan and the College of Engineering. I'm looking at the Danes and University of Michigan, Jack here. I think this is so important. Sincere thanks to University of Michigan for giving faculty members like myself the freedom to do this kind of crazy stuff. And for encouraging and supporting entrepreneurship. It used to be frowned upon 25 years ago, but it's so different now. And for that, I'm very thankful for doing that. So I think looks like everybody's ready to go. Thank you. It's wonderful.
Yes, sir.